Hello everyone, for today's video, we are going to solve a sample problem in chapter 12, heat transfer by radiation. Problem 12.1, black body radiation. A 3.2 mm thick glass window transmits 90% of the radiation between 0.3 and 3 meter. It is essentially opaque for radiation at other wavelengths. Determine the rate of radiation transmitted through a 2 by 2 meter glass window from blackbody sources at A 5850 Kelvin and B 1020 Kelvin. So step 1, in order to determine the rate of the radiation transmitted, we need to use the following equation. Et is the rate of transmitted radiation. Delta F is the fraction of radiation emitted between two given wavelengths. N is transmitting efficiency, and Et is the total blackbody radiation emission. So before we start determining the needed parameters, we first need to calculate the surface area of the window. So area is equals to 2 times 2, so we have 4 meters squared. So A, in order to determine the fraction of the energy that falls into the given range, we need to use the Weyens displacement law, table 12-2. Since the range extends from 0.3 m to 3.0 mu m, we have um, thermal conductivity 1 temperature is equals to 0.3 times 5800, so we have 1740 mu m times Kelvin. And for our thermal conductivity temperature is equals to 2 is equals to 3 times 5800, so we have 17,400 mu m times Kelvin. Step 2. Since the volume of thermal conductivity temperature is not exact, we need to interpolate the coefficient values between upper and lower values of thermal conductivity temperature using the table 12-2, like the F thermal conductivity is equals to 0.019718 plus 0.039341 minus 0.019718 times 1740 minus 1600 over 1800 minus 1600. So our F thermal conductivity of substances is equals to 0.03345. Since the value of thermal conductivity to temperature is not exact, we need to interpolate the coefficient values between upper and lower values of thermal conductivity temperature 2 using the table 12-2, like F is equals to thermal conductivity of substance is equals to 0.973814 plus 0.980860 minus 0.973814 times 17,400 minus 16,000 over 18,000 minus 16,000. So our F thermal conductivity is equals to 0.97875. So the fraction of the energy that falls into the given range is change of F is equals to F thermal conductivity minus F thermal conductivity 1 is equals to 0.9453. So to determine the total blackbody radiation emission, we use the Stefan-Boltzmann law. So EB times T is equals to area times t raised to 4. So we have 5.67 times 10 raised to negative 8 times 4 times 4 times 5,800 raised to 4 is equals to 2.567 times 10 raised to 8 watts. Step 3. So the rate of transmitted radiation is ET is equals to 0.9 times 0.9453 times 2.567 times 10 raised to 8. So the final answer, or the emissivity is equals to 218,400 watts. Therefore, the final solution is ET is equals to 218,400 watts. So for our B, we have the thermal conductivity of T is equals to 0.3 times 1000. So we have 300 mu m times Kelvin. And for our thermal conductivity, temperature 2 is equals to 3 times 1000. So we have 3000 mu m Kelvin. So the value of F, thermal conductivity, which corresponds to the value of thermal conductivity temperature, is F thermal conductivity equals to 0. So the value of F thermal conductivity, which corresponds to the value of thermal conductivity 2 temperature, is F thermal conductivity 2 equals 0.273232. So for our step 4, the fraction of the energy that falls in the given range is change in F is equals to F minus F1. So we have 0.273232. To determine the total black body radiation emission, we use the Stefan-Boltzmann law. So we have emissivity times T is equals to the cross-sectional area times T raised to 4 is equals to 5.67 times 10 raised to negative 8 times 4 times 1000 raised to 4. So EB is equals to 226,800 watts. So the rate of transmitted radiation is E is equals to 0.9 times 0.273232 times 226,800. So our ET is equals to 55,772 watts. Therefore, the final solution is E is equals to 55,772 watts. So that's all for today's video. Thank you for watching, guys.